Today we're going to be talking about the characteristics of air filters and how that affects their efficiency with a focus on the types of air filtration systems you would buy for the home. So let's start with, why do people buy air filters? What is it that the air filters are supposed to filter? Well, they're all forms of particles floating around in the air, and one type is allergens, such as pollen, mold, and skin flakes from pets. Some people also worry about dust levels in their home getting resuspended due, for example, to cleaning activities. In other cases, there are combustion sources inside the home. Things like cooking or cigarette smoking can add to the airborne particle levels. And finally, in some cases, people are filtering the indoor air to protect themselves from a very polluted environment outdoors. So let's talk a little about these particles and how they're the same and how they're different. I first want to draw your attention to the fact that they are a very wide range of sizes or diameters. To give you context, human hair is somewhere between 50 and 150 micrometers in diameter. And here are how some of the other common particles indoors, how they compare, with things like house dust and pollen tending to be larger sized particles. Whereas things like airborne smoke tending to be all very, very small, smaller than 1 micrometer. So which filtration system should you buy? What happens if you go to the store and shop for a portable filtration system? Well, you'll see a lot of advertising claims, and one category focuses on what types of these indoor air pollutants it removes. And so you'll see claims about removing up to 99% of dust, getting rid of allergens, catching pollen and pet dander, reducing smoke levels. And then the other type of claim focuses on the characteristics of the filter itself, talking about how efficient it is, or just saying it's a high efficiency filter. You'll see a lot of claims related to something called HEPA. That the filter is HEPA type or HEPA-like or a HEPA-style filter. I've also seen microfiltration referred to these filters. So how the heck do you know which one is the best? Well, to figure that out, I need to tell you a little bit about what filters are made of, how they're composed. And so this picture here shows a filter and the fibers in the filter, and you see that there's lots and lots of very tiny fibers. This happens to be a true HEPA filter, and HEPA stands for high efficiency particle arrestance, and you can think of arrestance as stopping. This is magnified 1,000-fold, and so each of these fibers you see are around 1 to 4 micrometers in diameter. And what you're wanting to collect are a wide range of particle sizes. Remember, the smoke particles were very small, on up to particles that are as big as 10 micrometers. And to give you an idea, that little red dot there shows how a 10 micrometer particle would look being captured by this filter. So if you look at how efficient filters are as a function of particle size, you'll see that it varies with size. So what we have here in this plot is we have particle diameter on the x-axis and the efficiency of the filter, that is the fraction of particles it will be able to collect, on the y-axis. And this is very typical in that the filter does a good job of catching very, very small and rather large particles. What it doesn't do such a good job of is these middle range particles, the 0.1 to 1 micrometer size. So you may say, well, what's going on? I can imagine how big particles get collected, but how are the little tiny particles collected? Don't they go right through the filter? Well, there are 3 different mechanisms via which filters can collect particulate matter, and I want to talk about each of them, as illustrated in this slide. The first one is impaction. And as you see, that's number A, so that's referring to a very big particle. And you see that very big particle running straight into the filter fiber. All the green lines you see are showing the path that the air follows as it goes around the filter fiber. And the problem this big particle has is it can't go with those turns in the air. Instead, it tends to go straight ahead and be collected on the filter fiber. If you'd like to think of a car analogy, this would be like a head-on collision into like a pole, where you don't have time to veer around the object. So impaction involves large particulate matter where there's too much mass to change direction. The next one illustrated here, B, is an example of interception. And so particle B is a little smaller than particle A. You can see that it is managing to follow those air paths, those streamlines going around the filter fiber. And it should have made it around. It was so close, but it was a little too wide, so it brushed up against the filter fiber. And so going back to a car analogy again, this is like sideswiping. You thought you were going to make it through in between two other cars, but you brush up against one of them because you were a little wider than you thought. So interception is important for medium-sized particles, and it has to do with their width. Even though they can change direction, they may still brush up against the filter fiber. Finally, we get down to C. And C is a teeny tiny little particle. And so you may think, well, that can follow those streamlines, those air paths really, really well. What's going on? Why is it zigzagging around instead? Well, this particle is so small that every time a gas molecule runs into it, it bounces off a little bit. And so its path is actually quite zigzaggy. And the tendency is for it, in all the zigzagging, to accidentally wander into and stick to a filter fiber. And so these collisions with gas molecules become an important reason why these very small particles are removed well. So this is how the plot looks again for particle size. And so now what you know is way over on this side here, what's being shown is this removal via diffusion. And the rule of thumb is the smaller the particle, the more energetically it's going to bounce off those collisions with gas molecules, and therefore the more efficiently it's going to be collected. On the far side, we see an increase in collection with particle size because the bigger the particle, for the larger size particles, the greater the removal via things like impaction and interception. The other thing you note here is there's now different types of filters represented. And so some filters are able to collect much more efficiently than others, but in every single case, usually the minimum is around the 0.2 to 0.3 micrometer range. If you're talking about something that is now called a true HEPA filter, that's that green line way up at the top. And that's because to be called a true HEPA filter, you have to have it collect at least 99.97% of all the particles passing through, no matter what the size of the particle. And so when they use the term HEPA-like, it's not very HEPA-like at all. It's dipping down to a value a lot lower than 99.97% efficiency. All right, well then let's loop back and see what this means for the different types of indoor particles we might like to collect. And what I've done here is line this up with our earlier list so that we can see how efficiently these different types of indoor particulate matter are collected. And so you can see we're going to get a good job of collecting things like pollen and house dust. But when you get down to smoke-type particles, the collection efficiency can be much poorer. So that's a really complicated plot. If you went to the store, you would not see this plot displayed on the packages. Instead, what they do is they give you a single number, a single value that they're reporting as the efficiency of their filter. And the problem is there's several different categories or ways of measuring efficiency as a single particle number. And so the first one I'm showing is called arrestance. And remember, that means just stopping the particles. This is very good, or is focused on how well the filter stops very large particles, say like soil dust particles. And so the little circle over there is showing you that most filters are going to have a very good efficiency in terms of their arrestance efficiency, because we're only focusing on those bigger particles. There's a second measure called dust spot efficiency that was meant to simulate or resemble outdoor particulate matter. So it covers a range of sizes, and then you come up with an average number based on that. And then there's yet another measure called DOP efficiency, where they're just focusing on one size of particle, the 0.3 micrometer particle. That's similar to smoke, but the other reason for focusing on that size is that's often near the minimum. And so that is giving you a measure of what the minimum efficiency is going to be for that filter. These are a lot of different measures. It's kind of confusing. Usually the packaging is not telling you which measure they're reporting. So they've come up with one more measure that kind of combines or relates these measures to each other. This is called the MERV, which stands for Minimum Efficiency Reporting Value. The MERV is here plotted on the x-axis versus the removal efficiency. And what you're seeing for each MERV value is what corresponding efficiency you would expect to get for these measures, such as dust spot efficiency and DOP efficiency. And now you can see how different some of these numbers are. You might see a 97% removal efficiency reported that's based on arrestance. And you can see that 97% value corresponds to just 10% removal of smoke particles. So you have very different values. And if you're looking for a really true quality HEPA filter, the MERV value is going to be at least 17. Anything below 17 is not classified as a true HEPA filter. And there's one other measure, a very different type of measure you might also see on packaging. This is called the clean air delivery rate, or sometimes the effective cleaning rate. And the idea behind that is they're telling you what volume per time of 100% clean air you're getting delivered from different devices. It sounds great, but now we get down to they're reporting not one but 3 different CADR values based on different parts of the size range. And so they'll report a clean air delivery rate for pollen, and that's focusing on particles in the 5 to 11 micrometer range. They'll report a second number for dust particles, and they'll report a third CADR that is for smoke particles. So you can see you might get quite different CADR numbers depending on whether they're focusing on pollen or on smoke. So let's do an example to see how you might calculate a CADR value. So I've given you an example of 2 filters here. Filter number 1 has a nice high flow rate passing through it, but not such a good efficiency. The second filter is operating at a lower flow rate, but a higher efficiency. We're going to calculate the clean air delivery rate by taking the removal efficiency times the flow rate. And so for each of these, when you calculate it out, you get the same number. 16 cubic feet per minute of clean air is being delivered by each of these filters. Well, is that a good number or not? 16 sounds kind of high. Well, this is one categorization that has been done of the clean air delivery rates. If your clean air delivery rate is below 10, it's pretty much not distinguishable from allowing gravity to have the particles settle out. Anything less than a value of 75 is viewed as poor, and that's because if you put this filter inside a small bedroom, it would take more than 16 hours to completely clean all the air in that bedroom. And you really need to get up to numbers of greater than 350 before it's viewed as an excellent filter for the indoor environment. So in this example, neither filter is really worth buying. Neither of them is delivering anything close to good quality cleaning. So all this we've talked about so far involves new filters. But of course, you're going to be using your filter, and your filter is going to be accumulating more and more particulate matter. And so what happens? What happens is that the filter performance changes. And there's some good news and bad news. Let me tell you first the good news. The good news is as you collect more particles on the filter, your collection efficiency increases. And the reason for that is that the particles you've collected on the individual filter fibers make those fibers bigger, make the gaps between the filter fibers smaller, and that enhances the ability of the filter to collect more particles. So that's the good news. Of course, there's bad news as well. And the bad news is that the flow rate through the filter is going to decrease. And the reason it's going to decrease is we're moving air through the filter using a pump or a blower. And when you have more and more obstructions to the flow, the pump or blower is not going to be able to move as much air per unit time through the filter. And so the result is that it's really expected that your clean air delivery rate will decrease with time, and sometimes that decrease can be quite substantial. So that's one bit of bad news, but alas, I'm not done yet. Another important thing with a filter is how it seals into the filter holder. So far, we've been talking just about the filters. Now we're going to talk about the filtration systems. And one aspect of the filtration system is wanting the filter to fit really snugly into its spot, into its filter holder. And actually, typically, filters in residential air cleaners fit rather loosely in their filter holders. And so over further on the right, I've drawn a more typical example where you now see that there's a gap between the filter and the filter holder. So why is that a problem? Well, some of the air is going to flow through the gap instead of through the filter. And so you see this little red arrow here going up and around. And so instead of having all green arrows, all clean air coming out the other side, you've got a little bit of dirty air sneaking through. And as more and more particulate matter builds up on the filter, it becomes more and more favorable for the flow to bypass the filter and not get filtered at all. And so as the more and more PM is collected, you're going to get more and more of this bypass problem. So what does that mean for our collection efficiency curves? It means even if you start with a pretty good air filter, if you've got a bypass problem, your original collection may look more like this blue line than the red dashed line above it. And that's kind of bad news because now it means you're not even collecting the house dust and pollen as well. And as the filter becomes more loaded, this line is going to just keep moving down as more and more of the air circumvents around the filter. So, in summary, wanted to let you know that the descriptions of the filters on the filter system boxes are often misleading. They use phrases like up to 99%. They may be focusing on particles like house dust or only particles 2 micrometers or larger. They may list a variety of types of particles, types of dust that they're able to collect without any information on how efficiently they collect them. And they may note in some cases that, well, the filtration efficiency they're reporting is for particles that pass through the filter, not including this bypass problem. And then the other bit of bad news is that the clean air delivery rate decreases with time as the particulate matter builds up on the filter. This is a CADR number for smoke. And remember, 72 is less than 75. So this, in fact, is representing what would be considered a poor removal efficiency for smoke particles. That's it. Are there any questions?